Which of the following statements is true about linear SVC in sklearn? A linear SVC is a linear model for classification that uses a hinge loss function. B. Linear SVC is a linear model for classification that uses a squared hinge loss function. C. Linear SVC is a linear model for classification that uses a logistic loss function. D. All of the above. Correct. Font style font size 18 solution font style font size 14 linear SVC in sklearn is a linear model for classification that uses a hinge loss function. This function is designed to encourage correct classification and penalize misclassifications. However, the loss function in linear SVC can be modified using the font color blue loss load font parameter. LTBRGT. LTBRGT. Font color blue loss hinged font. This is the default value and uses the standard hinge loss. Font style font size 18 hinge loss function font style font size 14 hinge loss is a key component of support vector machines SVMs and is used in linear SVC. It's designed to penalize misclassifications and encourages correct classification. The basic idea is that the loss is 0 for correctly classified samples and increases linearly for misclassified samples. The loss is minimized during training to find the optimal hyperplane that best separates the classes. Font. Correct. Font style font size 18 solution font style font size 14 linear SVC in sklearn is a linear model for classification that uses a hinge loss function. This function is designed to encourage correct classification and penalize misclassifications. However, the loss function in linear SVC can be modified using the font color blue loss load font parameter. LTBRGT. LTBRGT. Font color blue loss squared hinged font. This uses the squared hinge loss function, which penalizes misclassifications more strongly than the standard hinge loss. Font style font size 18 squared hinge loss function font style font size 14 The squared hinge loss is a variation of the standard hinge loss that penalizes misclassifications more strongly. This can lead to faster convergence in some cases, but may also make the model more sensitive to outliers. In linear SVC, this option is available using the font color blue loss squared hinged font parameter. Font. Correct. Font style font size 18 solution font style font size 14 linear SVC in sklearn is a linear model for classification that uses a hinge loss function. This function is designed to encourage correct classification and penalize misclassifications. However, the loss function in linear SVC can be modified using the font color blue loss load font parameter. LTBRGT. LTBRGT. Font color blue loss local font. This uses the logistic loss function. It is a convex function and does not require regularization. Font style font size 18 logistic loss function font style font size 14 The logistic loss function is commonly used in logistic regression models. In linear SVC, it can be used through the font color blue loss local font parameter. Unlike hinge loss, logistic loss is a convex function and does not require regularization. This can make the model less prone to overfitting. Font. correct. Font style quad font size 18 squat solution font font style quad font size 14 squat linear SVC in sklearn is a linear model for classification that uses a hinge loss function. This function is designed to encourage correct classification and penalize misclassifications. However, the loss function in linear SVC can be modified using the font color blue loss load font parameter. LTBRGT. LTBRGT. Therefore, all of the statements are true, making option D the correct answer. Font. Font style quad font size 18 squat linear SV font style quad font size 14 squat linear SVC is a linear model for classification in sklearn. It uses a hinge loss function for training, which encourages correct classification and penalizes misclassifications. It's particularly effective for high-dimensional datasets and binary classification problems. Font. Font style quad font size 16 squat D. All of the above. Font. Let's consider a binary classification problem where we have two classes, positive and negative. We have the following data points with their corresponding labels. Feature 1 Feature 2 label 1 2 positive 3 4 positive 5 6 negative 7 8 negative. Using linear SVC with the default hinge loss, we can train a model to find the optimal hyperplane that separates the positive and negative classes. The hinge loss function will penalize any misclassifications, pushing the data points closer to their correct side of the hyperplane. This hyperplane represents the decision boundary, where points above it are classified as positive and points below are classified as negative. Alternatively, we can use the squared hinge loss, which penalizes misclassifications more strongly. This could lead to a more robust decision boundary that better generalizes to unseen data. Finally, we can use the log loss, which is a convex function and does not require regularization. This option can be beneficial for datasets with high dimensionality, as it can help to prevent overfitting. Font style quad font size 14 squat 1. Text classification Albrecht. Identifying the category of text documents. Example spam detection, sentiment analysis. Font. Font style quad font size 14 squat 2. Image classification Albrecht. Classifying images based on their content. Example recognizing objects, faces. Font. Font style quad font size 14 squat 3. Fraud detection Albrecht. Identifying fraudulent transactions or activities in financial data. Font. Font style quad font size 14 squat 4. Medical diagnosis Albrecht. Assisting in the diagnosis of diseases based on patient data. Example lab results, medical history. Font. Which of the following statements is true about linear SVR in sklearn? A linear SVR is a linear model that predicts continuous values. B. Linear SVR uses a hinge loss function for regularization. C. Linear SVR is primarily used for classification tasks. D. All of the above. Linear SVR is a linear model, and as such, it predicts continuous values based on a linear relationship with the input features. Linear SVR, being derived from SVM principles, leverages the hinge loss function to regularize the model, preventing overfitting and improving generalization. Linear SVR is designed for regression tasks, where the goal is to predict continuous values. While SVM is a classification model, linear SVR builds upon its principles for regression purposes. The correct answer is D. All of the above, because all the above statements are true. D. All of the above predicts continuous values based on linear relationship with input features. A supervised learning model that finds the optimal hyperplane to separate data into classes. Linear model for regression tasks that uses SVM principles for finding the optimal hyperplane that minimizes the error between predicted and actual values. A loss function used in SVM models to penalize misclassifications. Techniques used to prevent overfitting by adding a penalty term to the loss function. Predicting stock prices. Forecasting sales. Estimating housing prices. Analyzing customer churn. Predicting energy consumption. Estimating loan risk. Let's say you have a dataset with house prices and features like size, location, and number of bedrooms. You want to build a linear SVR model to predict house prices based on these features. Here's a simplified example with hypothetical data. Size SQ foot, location code, bedrooms price USD 2001 300,000 1,500 to 250,000 2,500 400,000 1,800 to 350,000. Using linear SVR, you train a model with this data. You would then input new features of a house, example size 2200, SQ Fort, location 1, bedrooms 3, and the linear SVR model would predict the house price based on the learned linear relationship between the features and price. The model learns a linear equation of the form: price W1, size W2, location W3, bedrooms B, where W1, W2, W3 are the weights for each feature, and B is the bias term. The model tries to find the best values for the weights and bias to minimize the difference between predicted and actual house prices. This involves finding the optimal hyperplane, in this case, a line in the multidimensional space of features. Python. From sklearn.svm, import linear SVR. Model linear SVR C 1.0, epsilon 0.1. Model.fitStrain, atrain. epred model.predictStist. This code demonstrates how to use linear SVR in scikit-learn. It first imports the linear SVR class, then creates an instance of the model with hyperparameters like C regularization parameter and epsilon tolerance for error. The model is then trained on the training data strain, atrain, using the fit method, and predictions are made on the test dataStist using the predict method. The predicted values are stored in epred. What is the primary advantage of using new SVC over SVC in scikit-learn's SVM implementation? A new SVC is faster for large data sets. B. New SVC offers enhanced robustness to outliers. C. New SVC provides direct control over the number of support vectors. D. All of the above. Correct. New SVC often exhibits better performance in terms of speed, particularly when handling extensive data sets. This stems from the fact that new SVC optimizes a different objective function than SVC. It focuses on controlling the fraction of support vectors, potentially leading to faster convergence in the optimization process. 17. Speed advantage. New SVC often proves faster, especially when dealing with massive data sets. Correct new SVC demonstrates superior resilience to outliers compared to SVC. This is achieved by new SVC's ability to manage the number of support vectors. By controlling the fraction of support vectors using the new parameter, new SVC can mitigate the influence of outliers on the decision boundary. It essentially helps prevent outliers from disproportionately skewing the model's predictions. 18 Outlier robustness. New SVC exhibits superior resilience to noisy data points, making it ideal for scenarios where outliers are a concern. Correct new SVC provides direct control over the number of support vectors via the new parameter. This parameter sets the fraction of support vectors that will be selected during model training. This allows for more fine-grained control over model complexity, especially in data sets with a large number of data points, potentially leading to a more efficient model. 19 Control over support vectors. New SVC empowers the user to directly specify the fraction of support vectors represented by the new parameter, offering fine-grained control over the model's complexity. Correct. All of the above statements accurately reflect the advantages of new SVC over SVC. New SVC combines the benefits of speed, outlier robustness, and direct control over the number of support vectors, making it a powerful tool for tackling various machine learning challenges. 14 Font style quote font size 16 quote d. All of the above. Font d. All of the above. In SVM, support vectors are the data points that lie closest to the decision boundary and influence the model's prediction. They are crucial because they directly shape the separating hyperplane that divides the data into different classes. Essentially, they are the data points that contribute most significantly to the model's learning. 22 Font style quote font size 16 quote support vectors load font. Imagine a scenario where you are building an image classifier to distinguish between cats and dogs. The support vectors in this case would be the images of cats and dogs that lie closest to the decision boundary, the line or hyperplane that separates cat images from dog images. These images would play a critical role in defining the model's ability to classify new images accurately. Outliers are data points that deviate significantly from the general trend or distribution of the data. They can be caused by errors in data collection, measurement, or simply unusual observations. Outliers can negatively impact the performance of machine learning models if not handled appropriately. They can distort the decision boundary, leading to inaccurate predictions. 24 Font style quote font size 16 quote outliers load font. Let's say you are developing a model to predict house prices based on various features like size, location, and number of bedrooms. A house with an unusually high price compared to others in its area would be considered an outlier. If this outlier is not handled correctly, it could influence the model to overestimate prices for other houses in that area. The decision boundary is the line or hyperplane that separates data points into different classes in a classification problem. SVM aims to find the optimal decision boundary that maximizes the margin between classes. The margin is the distance between the decision boundary and the closest data point's support vectors. A larger margin generally indicates better generalization and less sensitivity to noise or outliers. 26 Font style quote font size 16 quote decision boundary font. Consider a scenario where you are building a spam detection system. The decision boundary would be the line or hyperplane that separates spam emails from legitimate emails. The goal is to find a decision boundary that maximizes the margin between spam and legitimate emails, ensuring that the model can reliably differentiate between them. The new parameter is a hyperparameter in new SVC. It controls the fraction of support vectors that the model will select during training. A smaller new value generally leads to a less complex model with fewer support vectors. This can be beneficial when dealing with large data sets, as it can improve computational efficiency and potentially reduce the risk of overfitting. Conversely, a larger new value might result in a more complex model with more support vectors, potentially capturing more nuances in the data. 28 font style quad font size 16 psquot new parameter font. Imagine you are training an SVM model to classify customer reviews as positive or negative. By adjusting the new parameter, you can control the number of support vectors reviews that the model considers crucial. A smaller new might lead to a simpler model that focuses on only the most impactful reviews, while a larger new might create a more complex model that takes into account a broader range of reviews. SVM, particularly new SVC, offers a robust framework for tackling various real-world classification problems. Its flexibility and ability to handle complex datasets make it suitable for a wide range of applications. 30 font style quad font size 16 psquot use case font. Image classification. Imagine an application that automatically identifies objects in images like cars, pedestrians, or traffic signs. New SVC's ability to handle complex patterns and its robustness against noise and variations in lighting make it well suited for this task. Spam detection. New SVC can be employed to filter out spam emails by learning the patterns that characterize spam messages. This is particularly helpful because spammers often try to disguise their messages to evade detection. Fraud detection. New SVC can be used to detect fraudulent financial transactions. The model can learn the patterns of legitimate transactions and identify those that deviate significantly from the norm, potentially flagging suspicious activity. Which of the following statements is true regarding new SVR? A. It is a nonlinear SVM algorithm used for regression. B. It is a linear SVM algorithm used for regression. C. It uses a fixed number of support vectors to define the regression function. D. All of the above. This statement is true. New SVR is a type of support vector regression SVR algorithm, which can be linear or nonlinear depending on the choice of the kernel function. It is used for regression tasks, aiming to find the best fit line that minimizes the errors between predictions and actual values. A. It is a nonlinear SVM algorithm used for regression.ltbrgt. This statement is also true. New SVR, like traditional SVR, can be linear or nonlinear depending on the kernel function. A linear kernel will result in a linear regression function, while a nonlinear kernel like polynomial or RBF will lead to a nonlinear regression function. B. It is a linear SVM algorithm used for regression.ltbrgt. This statement is true. New SVR differs from standard SVR by utilizing a fixed number of support vectors, as indicated by the new parameter. This fixed number contributes to its resilience against outliers, as it focuses on a predetermined set of influential data points. C. It uses a fixed number of support vectors to define the regression function .ltbrgt. This statement is true as all the previous statements are true. D. All of the above .ltbrgt. D. All of the above. Support vectors. These are the crucial data points that directly shape the decision boundary, or in this case, the regression function. They hold significant influence in determining the model's behavior. Kernel function. This function determines the complexity of the regression function. Different kernels, like linear, polynomial, radial basis function RBF, etc., offer varying levels of complexity and flexibility. New parameter. This parameter is unique to new SVR. It directly controls the number of support vectors used in defining the regression function. This number affects the model's robustness against outliers. A higher nu might result in more support vectors, potentially reducing sensitivity to outliers, while a lower nu might lead to fewer support vectors, potentially making the model more prone to outliers. Regularization. This is a key technique to prevent overfitting. It controls the complexity of the model, ensuring it generalizes well to unseen data and avoids being overly influenced by the training data. Support vectors. The data points that directly influence the decision boundary regression function. LTBRGT kernel function determines the complexity of the regression function. Linear, polynomial, RBF, etc. LTBRGT new parameter controls the number of support vectors used. Higher nu more support vectors, potentially less robust to outliers. Lower nu fewer support vectors, potentially more prone to outliers. Regularization helps prevent overfitting by controlling the complexity of the model. LTBRGT New SVR finds applications in various real-world scenarios due to its ability to model and predict continuous values. Time series forecasting. Forecasting future values based on historical data is a key application. For instance, predicting future stock prices, sales, or weather patterns. Financial modeling. New SVR is utilized in financial modeling for predicting stock prices, interest rates, and other financial variables. It helps in risk assessment and asset allocation strategies. Machine learning. In general, new SVR can be employed in various machine learning applications involving the prediction of continuous values. This encompasses fields like image recognition, natural language processing, and medical diagnostics. Time series forecasting. Predicting future values based on historical data. LTBRGT financial modeling. Forecasting stock prices, predicting interest rates. LTBRGT machine learning. Predicting continuous values in various applications. LTBRGT The code snippet illustrates how to implement new SVR in Python using the scikit-learn library. From sklearn.svm import new SVR. This line imports the new SVR model from the scikit-learn library. Model new SVR kernel RBF, new 0.5, gamma scale, C1.0. This line creates an instance of the new SVR model, specifying the desired parameters. Kernel RBF indicates the use of a radial basis function kernel, a popular choice for nonlinear regression. New 0.5 determines the fraction of support vectors used. Gamma scale is a parameter for the RBF kernel, controlling its influence. C1.0 is the regularization parameter, balancing the trade-off between model complexity and error minimization. Model.fitStrain, train. This line trains the new SVR model on the training data strain, train. Predictions model.predictStist. This line uses the trained model to make predictions on new data stist, obtaining the predicted values predictions. LTBGT sklearn new SVR function from sklearn.svm import new SVR model new SVR kernel rv new 0.5 gamma scale C 1.0 model.fit strain a train predictions model.predicts. Which of the following statements are true about one class SVM for anomaly detection in scikit-learn sklearn? It uses a hyperplane to separate normal data points from anomalous ones. It can handle both linear and nonlinear decision boundaries. It requires labeled data for both normal and anomalous instances. One class SVM uses a hyperplane or a nonlinear decision boundary to separate normal data from anomalies. The hyperplane is a linear decision boundary, which is used when the data is linearly separable. Nonlinear decision boundaries are used when the data is not linearly separable, and they are created using kernel functions. True. Hyperplane. Kernel functions. Decision boundary. In a network intrusion detection system, one class SVM can be used to identify malicious traffic patterns that deviate from normal network activity. In a credit card fraud detection system, one class SVM can be used to identify fraudulent transactions that are different from typical spending patterns. In a medical anomaly detection system, one class SVM can be used to identify unusual patterns in medical data that may indicate a disease. One class SVM can handle both linear and nonlinear decision boundaries. For linear cases, it uses a hyperplane. For nonlinear cases, it uses kernel functions to map the data to a higher dimensional space where it becomes linearly separable. True. Hyperplane. Kernel functions. Decision boundary. One class SVM can be used to detect anomalies in image data, where the anomalies may not be linearly separable from the normal data. One class SVM can be used to detect anomalies in time series data, where the anomalies may not be linearly separable from the normal data. One class SVM can be used to detect anomalies in text data, where the anomalies may not be linearly separable from the normal data. One class SVM is an unsupervised learning algorithm, meaning it only requires unlabeled data for training. It learns the distribution of the normal data and flags deviations from this distribution as anomalies. False. Unsupervised learning. Anomaly detection. One class SVM can be used to identify unusual behavior in a system, such as a website or a network, without requiring labeled data about what constitutes malicious behavior. One class SVM can be used to detect anomalies in sensor data, such as temperature or pressure readings, without requiring labeled data about what constitutes a fault. One class SVM can be used to detect anomalies in financial data, such as stock prices or transaction amounts, without requiring labeled data about what constitutes fraudulent activity. All of the above. You are building a model to classify customer sentiments positive or negative based on their product reviews. You decide to employ SVC. What parameter primarily controls the trade-off between the model's complexity and its ability to generalize well? Kernel. C. Gamma. All of the above. Incorrect. The kernel determines the type of decision boundary. It doesn't directly control the trade-off between complexity and generalization. For example, a linear kernel results in a simple model with a straight-line decision boundary, while a polynomial kernel creates a complex model with a curved decision boundary. While the complexity of the kernel can influence the model's generalization, it's not the primary parameter. Incorrect. The C parameter controls the penalty for misclassifications. A higher C value leads to a stricter penalty, resulting in a more complex model that tries to fit the data more closely. A lower C value allows for more misclassifications, leading to a simpler model. While this impacts the model's complexity and generalization, it is not the only parameter. Incorrect. The gamma parameter influences the width of the Gaussian kernel in the case of an RBF kernel or the influence of each training example. A higher gamma value results in a narrower kernel, leading to a more complex model that overfits the training data. A lower gamma value results in a wider kernel, leading to a simpler model with better generalization. While this impacts the model's complexity and generalization, it is not the only parameter. Correct. All of the parameters influence the trade-off between complexity and generalization. The kernel determines the shape of the decision boundary, influencing the model's complexity. C controls the penalty for misclassifications, impacting the model's complexity. Gamma influences the width of the kernel, affecting the model's capacity to fit the data, thus impacting generalization. D. All of the above. The kernel function in SVC determines the shape of the decision boundary. Different kernels allow for different types of decision boundaries, leading to different model complexities. Creates a simple, straight line boundary. Effective for linearly separable data. Simple classification tasks where data points are clearly separated by a straight line. For example, separating emails into spam and non-spam categories based on keywords. Creates curved boundaries for more complex data patterns. It allows for nonlinear decision boundaries. Classifying handwritten digits where patterns are complex and not linearly separable. For example, differentiating between handwritten digits 4 and 9 which can be similar in shape. Creates flexible boundaries using a Gaussian function. It can handle nonlinear data well and is a popular choice for many applications. Image classification where features are complex and often nonlinear. For example, identifying different types of objects in a picture like cars, pedestrians, and trees. The C parameter in SVC controls the penalty for misclassifications. A higher C value leads to a stricter penalty, resulting in a more complex model that tries to fit the data more closely. A lower C value allows for more misclassifications, leading to a simpler model. Fraud detection where minimizing false negatives is crucial. A higher C value would help in identifying even subtle fraudulent patterns, leading to a more complex model but potentially higher accuracy. The gamma parameter influences the width of the kernel function, particularly in RBF kernels. A higher gamma value results in a narrower kernel, leading to a more complex model that overfits the training data. A lower gamma value results in a wider kernel, leading to a simpler model with better generalization. Text classification where capturing broader semantic patterns is important. A lower gamma value would help in identifying broader patterns in the text data, leading to a simpler model but potentially higher generalization. Which of the following statements are true about support vector regression SVR in sklearn? A SVR is a supervised learning algorithm used for regression tasks. B. SVR uses a kernel function to transform the data into a higher dimensional space. CSVR aims to find a hyperplane that maximizes the margin between the data points and the decision boundary. DSVR can handle both linear and nonlinear data. All of the above. Correct. This statement is true by definition. SVR is a type of support vector machine SVM specifically designed for predicting continuous target values. It falls under the umbrella of supervised learning because it learns from labeled data, where both the input features and the corresponding target values are provided. Supervised learning. Correct. This is true. Kernel functions are used in SVR to handle nonlinear relationships in data. By mapping data to a higher dimensional space, SVR can find a linear separation in this transformed space, effectively capturing nonlinear patterns. This allows SVR to model complex relationships that might not be linearly separable in the original input space. Kernel functions. Correct. This is also true, but with a twist. Unlike in classification SVMs, the margin in SVR represents the tolerance or tube around the regression line where points are considered correctly predicted. The goal is to find a hyperplane that minimizes the errors within this tolerance zone. Hyperplane. Margin. Correct. True. As mentioned earlier, SVR leverages kernel functions to address nonlinear relationships. For linear data, the linear kernel can be used, and for nonlinear data, various kernels polynomial, RBF, sigmoid can be employed. This flexibility allows SVR to adapt to different data characteristics. Linear data. Nonlinear data. Correct. Since all the previous statements are true, this statement is also correct. All of the above. Time series forecasting predicting future values of a variable based on its historical trend. For instance, forecasting stock prices, predicting sales figures, or analyzing weather patterns. Time series forecasting. Financial market prediction analyzing financial data to predict market movements, such as predicting the price of a cryptocurrency or forecasting the performance of a specific stock. Financial market prediction. Demand forecasting predicting future demand for products or services. This helps businesses plan production, inventory management, and marketing strategies. Demand forecasting. 1, 2, 2, 4, 3, 6, 4, 8. Let's consider a simple example where we want to predict the value of y based on x. Using SVR with a linear kernel, we can find a regression line that minimizes the errors within a specified tolerance zone. The goal is to find a hyperplane in this case, a line that balances fitting the data points while maintaining a certain level of generalization. Which of the following is not a use case for support vector regression SVR in machine learning? A. Predicting the price of a house based on its features. B. Forecasting stock prices based on historical data. C. Classifying emails as spam or not spam. D. Predicting the amount of rainfall based on weather patterns. True. Predicting house prices based on features like size, location, and amenities is a regression task, as the price is a continuous value. SVR is well suited for such predictions, making it a suitable use case. True. Forecasting stock prices involves predicting a continuous value price based on historical data. SVR is a powerful tool for time series forecasting, making it a suitable use case. false. Classifying emails into categories spam or not spam is a classification task. SVR is a regression algorithm, not designed for classification. We need a different type of algorithm like logistic regression or support vector machines SVM for classification. This makes it an unsuitable use case for SVR. True. Predicting rainfall, which is a continuous value, based on weather patterns is a regression task. SVR is suitable for making such predictions, making it a suitable use case. See classifying emails as spam or not spam. Regression and classification are two fundamental types of machine learning tasks. Regression is used to predict a continuous output variable. It aims to find the relationship between input variables and the output, allowing us to estimate the value of the output for new inputs. Predicting the price of a house based on its size, location, and other features. Predicting house prices, forecasting stock prices, estimating the amount of rainfall, modeling complex systems like traffic flow or energy consumption. Classification is used to predict a categorical output variable. It aims to assign input data points to predefined categories or classes. Classifying emails as spam or not spam, identifying handwritten digits, categorizing images into different types. Spam filtering, medical diagnosis, image recognition, customer segmentation. SVR is a supervised learning algorithm used for regression problems. It is a powerful tool for finding the optimal fit for data points, minimizing the error between predicted and actual values. SVR is a type of support vector machine SVM adapted for regression. It works by finding a hyperplane in the multidimensional space of the data points, which is then used to predict the output value. Time series forecasting stock prices, weather patterns, price prediction houses, cars, risk management, system modeling. 1, 2, 2, 4, 3, 6, 4, 8. Let's say we have data points 1, 2, 2, 4, 3, 6, 4, 8. The goal of SVR is to find a line hyperplane that best fits these data points, minimizing the error between the predicted and actual values. From sklearn.svm import SVR. x1, 2, 3, 4. y2, 4, 6, 8. SVRmodel SVRkernel linear. SVRmodel.fit x, y. Prediction SVRmodel.predict 3.5. Printf prediction for input 3.5 prediction 0. Here's how to use SVR in the popular scikit-learn sklearn library in Python. Import the necessary libraries. Create an SVR model object. Train the model using your training data. Make predictions on new data. From sklearn.svm import SVR. Load your data, replace with your data. Strain. Train. Stist. Create an SVR model. SVRmodel SVRkernel linear. Train the model. SVRmodel.fit strain, train. Make predictions. Predictions SVRmodel.predict stist. Which statement accurately describes the purpose of the L1 minc parameter in scikit-learn's SVM model? A. It determines the strength of the L1 penalty applied to the SVM's weight vector. B. It defines the minimum value for the C parameter during cross-validation, influencing the trade-off between model complexity and accuracy. C. It's a threshold for feature selection, eliminating features with weights below this value. D. All of the above. It adds a penalty term to the SVM's objective function, proportional to the absolute values of the weights. This encourages sparsity, forcing some weights to become zero, effectively selecting only the most relevant features. True. It serves as the minimum value for the C parameter during cross-validation. This ensures that the model explores a range of C values, potentially finding the optimal balance between complexity and accuracy. True. Since L1 regularization encourages sparsity, the L1 MINC indirectly affects feature selection. By finding the optimal C value during cross-validation, the model identifies and keeps only the most influential features, effectively eliminating less relevant ones. True. In the context of scikit-learn's SVM, the L1 MINC parameter is used to control L1 regularization during cross-validation. True. D. All of the above. It adds a penalty term to the SVM's objective function, proportional to the absolute values of the weights. This encourages sparsity, forcing some weights to become zero, effectively selecting only the most relevant features. Feature selection in high-dimensional datasets. Example: gene expression data. Improving model interpretability by reducing the number of features. Preventing overfitting in models with many features. Consider a linear SVM with weights W1, W2, W3. The L1 regularization term would be W1, W2, W3, where is the regularization strength? A higher value would encourage more weights to become zero. This parameter controls the trade-off between maximizing the margin, reducing model complexity, and minimizing misclassifications, improving accuracy. A larger C value leads to a more complex model, while a smaller C value encourages simpler models. Balancing model complexity and accuracy in image classification tasks. Finding the optimal trade-off between model performance and interpretability. Adjusting the model's sensitivity to outliers and noisy data. In SVM optimization, the objective function involves minimizing a loss term, example hinge loss, and a regularization term, example L1 or L2. The C parameter balances these two terms. A higher C gives more weight to minimizing the loss, potentially leading to overfitting, while a lower C gives more weight to regularization, potentially leading to underfitting. It serves as the minimum value for the C parameter during cross-validation. This ensures that the model explores a range of C values, potentially finding the optimal balance between complexity and accuracy. Automating the process of finding the best C value for an SVM model. Improving the robustness of the model to different data distributions. Optimizing the model's generalization performance on unseen data. During cross-validation, the L1 MINC sets the lower bound for the range of C values that the model explores. This helps in identifying the C value that results in the best performance on the validation sets. It serves as the minimum value for the C parameter during cross-validation. This ensures that the model explores a range of C values, potentially finding the optimal balance between complexity and accuracy. Evaluating the performance of machine learning models on unseen data. Selecting the best hyperparameters for a model based on its performance on validation sets. Estimating the model's generalization error, which is the error on unseen data. Imagine dividing your data into k-folds. In k-fold cross-validation, you train the model on k1 folds and evaluate it on the remaining fold. This is repeated k times, with a different fold held out each time. The final performance metric is averaged across all k iterations. Since L1 regularization encourages sparsity, the L1 MINC indirectly affects feature selection. By finding the optimal C-value during cross-validation, the model identifies and keeps only the most influential features, effectively eliminating less relevant ones. Reducing the number of features in a high-dimensional dataset, improving model efficiency and interpretability. Identifying the most important factors influencing a target variable, example predicting customer churn. Simplifying the model without sacrificing performance. Consider a dataset with 10 features, but only 3 of them are truly relevant for prediction. With L1 regularization, the model's weights for the irrelevant features will tend towards 0, effectively selecting the 3 most important features. This parameter controls the trade-off between maximizing the margin, reducing model complexity, and minimizing misclassifications, improving accuracy. A larger C-value leads to a more complex model, while a smaller C-value encourages simpler models. Preventing overfitting, which occurs when a model is too complex and learns the training data too well, leading to poor performance on unseen data. Balancing model performance and interpretability. Adjusting the model's flexibility to different data distributions. A simple model with fewer parameters, lower complexity, might not be able to perfectly fit the training data, but it will generalize better to unseen data. A complex model with many parameters, higher complexity, might fit the training data perfectly, but it will likely overfit and perform poorly on unseen data. This parameter controls the trade-off between maximizing the margin, reducing model complexity, and minimizing misclassifications, improving accuracy. A larger C-value leads to a more complex model, while a smaller C-value encourages simpler models. When a model performs very well on training data but poorly on unseen data. When a model learns the noise in the training data, making it less effective on new data. When a model is too complex and doesn't generalize well to new data. Imagine a model that perfectly fits the training data, achieving 100 accuracy. However, this model might have learned the specific patterns of the training data too well, and it will struggle to generalize to new data with different patterns.